Hello, my name is Aaryan Chatterjee, and this is my constant motion lab in Physics 2211. Before we get directly into the lab, I think it's important to understand what the lab is precisely covering, which is motion. Motion in physics is a fundamental concept that can be seen when an object's position changes over a certain amount of time, since that means the object must be moving. Now, in this lab, we will be using physics to analyze and determine an object's change in position while in motion. More specifically, this lab will be focused on comparing an observational model and a computational model to see how similarly or differently they describe an object that has constant speed in only one direction. Later in this presentation, we will see that both the computational model and observational model provide very close results, as we can see in this graph here. This indicates that the lab here is extremely important, as it shows us that both models are of acceptable quality and provides us with separate tested ways on how to examine an object's motion. However, before we get into lab specifics, I think it is important to understand some of the crucial physics principles and ideas utilized in the lab. Firstly, it is important that everyone understands Newton's first law, as it simply states that object in motion will stay in motion unless acted on by a force. And this applies to our lab, as we want our object to just continue to move with constant velocity, so we don't want any forces acting on the object in the experiment. Additionally, Newton's second law reinforces this idea, as it says force equals mass times acceleration. And since we want an object with constant speed for our experiment, there should be no acceleration, so we should have no external forces acting on the object. Furthermore, we can use Newton's second law to create a velocity update formula, which will be the way to define velocity in the computational model. And we will also use a position update formula in the computational model to find the object's position at many different times. Now, we must cover some important assumptions in the experiment, and one of them is that the object does not experience any net force on it in order to ensure that the object continues to have a constant velocity. This basically means that we will not be considering friction and air resistance on the object, since those forces would affect the object's speed in the computational model. Finally, we assume that the object only moves in the horizontal direction, and more specifically to the right in the positive x direction. On top of the assumptions, it is important to know that the system, which is what we will analyze, is simply the object used in the experiment, and everything else is the surroundings like the ground. Additionally, the object's initial position is at the origin and will be moving right, which is the positive x direction, as I just said. We will then analyze the ball for zero point 0.8 seconds total, with the experiment starting at when t equals 0 seconds, and the ball has an initial velocity of 2.885 meters per second, which I will discuss how I found. So, for the actual experiment, I rolled a basketball to the right and then ensured that the object's motion was filmed, and this is my finished video. Now, with that video, I then inputted it into an app called Tracker and analyzed the ball's motion by seeing where the ball was at different time intervals with respect to where the ball started. That gave me a chart of data relating to the object's position in the right direction, which I then inputted into Excel and made a graph out of, which you will see in the later slides. After I finished the observational model, I then decided to work on the computational model, but I ran into a problem where I needed to have the object's velocity to computationally find the ball's position at different times. Firstly, I looked at the observational model's data chart, which is shown to the left, and I found that the final position of the object in the x direction was 2.308 meters. So because I knew the object's final x position and the object's initial x position, which was 0 meters because it started at the origin, I found the average velocity of the object by doing final position minus initial position divided by time. And due to the fact that there's no forces on the object, the average velocity will be constant for the entire time period and will be the initial and final velocity. So after finding the initial velocity of the object, I was finally able to start my computational model, where I first had to set the ball's initial conditions. I set the ball's mass to 0.625 kg, the ball's initial position to 0 because it started at the origin, and the ball's initial velocity to the velocity I found in the last slide. I then started my model at t equals 0 seconds and made my delta t to 0.032 seconds in order to match the frame rate of the tracker app and the observational model. I then created a while loop that continued until the end of the time period, which was zero point 0.8 seconds. And in the while loop, I set the force to 0 and updated the velocity and position every delta t with the velocity and position update formula. After that, I ran my program, which gave me a table of position points, which I then graphed in Excel with the observational model. So now that I have the data of both models graphed, with the observational model being the points and the line in orange and the computational model being the points and the line in blue, I was able to properly compare both models. Looking at the graph, I came to the conclusion that both models are extremely similar results, since both of the model's position points were extremely close, indicating the computational model is extremely accurate like the observational model. However, there's one main difference, which was the fact that the computational model had position points a little below what the observational model had at the beginning, and the computational model had bigger position points at the end compared to the observational model. But this can be explained due to errors in my use of tracker, making the observational data vary a little, and due to the fact that friction may have slowed down the ball in the observational model and the computational model did not account for that. Moving on from the lab's data, it is important to note that the lab could have been done in a different way by flipping the axes. This is done by making the x positive direction actually be set to the left instead of the right, which would make the position data have the same magnitudes as it does now, but it would just be in the negative x direction. This would result in identical graphs as mine, but it would just be flipped so all the points would be in the negative x quadrant and the slope would be negative, and this can be seen in the example graph on the right. Additionally, another question that we must address is whether or not it would be possible to say how many forces were added together to give a net force of 0 in this case. And the answer is it is not possible. Although we know that the overall net force is 0, we cannot be sure about all the individual forces that acted on the ball, since there could be some unknown object in the surroundings that could have interacted with our basketball but got cancelled out by something else. That's it for my presentation. Thank you for listening.